Yeah, all right. Our next speaker is Martin van der Wilk, who will be talking about distribution generalization and sensitivities. Thanks.
All right, hi everyone. Yes, great to be here. So one reason I'm particularly happy to be here today is because I've been following the work of the algorithmic information theory community with great interest over recent years, but I haven't really had a lot of opportunities to interact with people that are directly doing research in this area. And I feel like my work has tons of overlap, so I'm really curious to hear your feedback and also hear what you think about some of the ideas that I'd like to share with you today. So in particular, I want to talk about out-of-distribution generalization and model size selection. And maybe to give a bit of a spoiler, basically all of the work that I find interesting and that I work on basically relies on a notion of Occam's razor. And I believe that if we can incorporate more of an explicit notion of Occam's razor into the learning that we can do, we can get new learning capabilities that are qualitatively different from what we currently get from simply minimizing training losses. So just to give two examples of concrete things that I've worked on in the past, I've worked on the question of deciding what architecture a neural network should use. For example, creating an architecture that can automatically decide whether it should be an MLP or convolutional, or whether it should have rotational equivariances in it or translational equivariances. And I believe that if you train a neural network explicitly to compress, then you can actually get this capability where architecture emerges automatically rather than having to be hard-coded in. And so there are a few papers like learning invariances using the marginal likelihood or learning layer-wise equivariances automatically using gradients, where we actually operationalize these ideas and come up with prototype learning algorithms that show these qualitatively different capabilities. In addition, we've also worked a lot on causal structure from observations. So similarly, we've basically followed a notion and embedded a notion of Occam's razor, and then we can actually find that there's a lot of evidence of causal direction in observational data, which is a lot more optimistic than what people usually say, that you can't determine causation from correlation. And that's true, but you can come up with a pretty good notion of causation from correlation. So as a little teaser of this, we've actually operationalized this in increasingly complicated and deep models. And what you see here is a filter bank of what starts off to be a randomly initialized multi-layer perceptron, MLP, fully connected. And you can see that what happens is it rotates the filters and organizes these filters into a rotational convolutional filter bank. So what you're seeing here is basically an architecture that's self-assembling itself into a rotationally convolutional architecture when it started off as being an MLP. And this is hard to do if you just train a model to fit the training data. And basically the notion that makes this work is a notion of Occam's razor. And I want to talk a little bit about where this notion can come from and how it relates to compression, and also how this relates to out-of-distribution generalization and growing and shrinking models. So the key question that I want to focus on in my work is, can we improve the deep learning training paradigm? Right? Because all of deep learning currently is based on optimizing parameters to fit the training data. And somehow this works really well. Somehow it does compress the training data somehow. But I want to ask the question, is this really the best that we can do? And I would argue that actually, there's some evidence that we might be able to do slightly better, right? So we might want better out-of-distribution generalization. We definitely want better continual learning. And we might also want automatic compute allocation. We might want our models to automatically tell us how much compute we need to allocate to them for them to suck all the information that is in the training data out of the training data. Now, my belief about how to solve these problems is that I think that the conceptual frameworks that we have are basically there, right? So the frameworks of Bayes and MDL, they're very similar, and they basically prescribe quantities that we should compute that allow us to solve these problems. So I basically think that the philosophy was largely done by those who came before us, and we just need to turn these prescriptions into practical methods. So yeah, we'll basically have to follow what was told to do before, but we'll have to do a few things differently. And one of the key things that I think we should do differently in order to get this notion of Occam's razor, we need a notion of volume in parameter space, not just data fit. And this requires integration, not just optimization. So this is a key computational challenge. And I think this is really what we should be focusing on in order to get these new capabilities that we might want. Yeah, so let's start by delving further into how we would want to improve deep learning. What's currently wrong with deep learning that we might want to do better at? So let's remind ourselves what deep learning actually does. So most of machine learning, most of deep learning is just curve fitting. Like, it's amazing what you can do with this, but ultimately you've got a training data set of inputs and outputs, and we want to find some kind of function that allows us to associate an output with any input. And we want the function that we find to do well on future inputs, which are different from our current inputs. So we want our model to generalize. Now, neural networks are just a way to parameterize these functions, and yeah, there are learning procedures that select a function from the set of functions that we can consider. So when we design a neural network, we basically follow a few stages. So first, we fix an inductive bias. First, we fix a connectivity structure, which we call an architecture. For example, we fix fully connected models and convolutional models. And this choice, this inductive bias, basically determines how we predict at points that we haven't seen before, given the points that we have seen before. But that's fixed once we create an architecture. After we select a rough architecture, we then fix the network size and determine how many neurons it has. And then during training, with those two things fixed, we just change the weights of this architecture to minimize some loss on our training data set. So all we require from a network is that this function goes nearby the points that were given. Now, this leaves us with a question: how should we generalize? And I usually say, how should we generalize out of distribution, just to indicate that we're not just interested in generalizing nearer points, but intuitively we might want to generalize far away from our training points as well. Now, here's a little toy example of one particular neural network with a particular activation function, and the two moons data set, and I basically plot what the predictions are from this neural network. Technically, I've even made it a Bayesian neural network, so I quantify uncertainty very well, and I've done the inference very, very well here. And what we see is that far away from the training data, we're completely ignorant about what class we want to use. So white indicates a 50-50 probability of predicting. Now, here's a different neural network with a different activation function, with a totally different way of predicting everywhere else. The only difference between these neural networks is the activation function, and it creates a very different inductive bias. Now, when designing any machine learning technique, we have to make a choice about which one of these two methods we're going to choose. So we can ask the question, well, which solution generalizes better out of distribution? Well, it's a trade-off, right? So this solution basically is cautious. So it might lead you to make cautious decisions, which might lead you to avoid doing something horrendously wrong. But this way of generalizing at least can be right, right? So this way of generalizing is never going to be actually right because it's always uncertain. Whereas at least this way of generalizing, it takes a bit of a risk, but it could actually be right. Yeah, which solution has correct or better uncertainty? Well, I would say they're just different, but we have to choose one way of generalizing or the other. Now, the other question that we can ask is, can current learning procedures actually distinguish between these two solutions? So let's say we create one bigger neural network that adds these two solutions together, and then we train those weights. Can our current training loss that just tries to fit the data even have a preference about whether it prefers one or the other? Or will it just not distinguish between these two? Well, I basically argue that, okay, yeah, so there are a few things that we can observe from that little example. The first is that inductive biases matter because they do actually give different predictions. They generalize differently, particularly far away from the training data. And you cannot generalize while also being uncertain, right? So in this example, we chose uncertainty. And in this case, we made a prediction that could be right. But if you want to be right, you have to make a strong prediction. So you can't generalize while also being uncertain. Prediction specificity and certainty are trade-offs. Now, one thing that we also can see from this example is that both models have the same fit on the training data set. So our training loss won't actually distinguish between one model or the other. So if we are to answer this question about which way we want to generalize out of distribution, we're going to need a different principle, a principle that can distinguish between the two ways of generalizing. So if we want to solve or do better at out of distribution generalization, I would argue that we at least need a procedure for distinguishing between these two different ways of generalizing. Interestingly, Bayes and MDL do actually distinguish between inductive biases. And it's simply for the reason that models that fit the training data the same way may compress them differently. So if I choose between those two models that I showed earlier based on an MDL or a Bayes criterion, it actually prefers the solution that generalizes aggressively, right? That says this whole region is more likely to be the red class than the blue class. So it chooses the solution that at least could be right. Now, when you see this solution, you could ask the question, well, okay, if we choose this aggressively generalizing solution, that generalizes out of distribution, don't we risk making huge mistakes, right? So for example, you could imagine it is totally possible that the underlying problem that generated this data has a blue cluster up there. So what would happen in a case like that? Well, basically, what happens in a case like that is if we keep the model fixed, then we will make the wrong prediction and we'll keep making the wrong prediction over and over again. So that is a really bad thing to happen. But if we want to have a shot at generalizing, we must take this risk. But interestingly, there is a solution, and it's actually the solution that Bayes and MDL will tell you to do, which is that you shouldn't keep your model fixed, right? So if you do see a blue point up in that top left corner, what should you actually do? Well, you should update your model. And if you do what Bayes and MDL tell you to do, you get this solution, and even a single blue data point in the top left corner will completely shift the model that's preferred by our criteria to the one that is uncertain everywhere. So the point being, training losses don't distinguish between these models. We need a criterion that does distinguish between these training models, and Bayes and MDL, I think, basically already do the right thing out of the box. And if we want to do this out of distribution generalization, then one way to mitigate these risks is model updating, so that if we make a mistake, we don't make this mistake over and over again, right? So it's okay to take a risk when generalization, when generalizing out of distribution. It's okay to make a mistake, but it's not okay to make this same mistake over and over again. And the way to do that is to do continual learning. So I would say that there's a second thing that we want, which is that we need methods that can do continual learning to mitigate the risks of out of distribution generalization. The two problems are intimately related with each other. Okay, so that leads to a third question that is intimately related with those previous two questions. And that's that if you do continual learning, you need to answer the question, how big should your model be? Right, so I said earlier that our current methods basically fix a model size, and then you do your gradient descent. But when you're doing continual learning, you can't expect your model to always be able to learn more novel data and continuously remember it without forgetting the past or losing plasticity without growing the model, right? So if you want a model that can actually incorporate new data, you need some kind of way of addressing changing the model capacity as it sees more data. Otherwise, you're stuck with just making models the worst case possible size, which is wasteful. So the third goal that I want to address is we need a procedure for automatically selecting the model size, possibly even throughout training, so that we can respond to this additional data that we can get, so that we can deal with the required risk-taking that out-of-distribution generalization requires us to do. So to show another example about why model size and generalization are actually intimately related, the two actually influence each other. So in our current procedures, where we just fit based on training loss, the model size that we choose actually influences how a model generalizes out of distribution. So for example, if you create an architecture that could either be an MLP or a CNN, if you make both these models small, then a small MLP won't fit MNIST, for example, but a small CNN will. And then, training with the training loss will select the model with the right inductive bias. But what happens if you include a very large MLP in the set of possible models that you want to consider? Then suddenly a very large MLP can fit the training data as well. And then you lose the ability to choose the right way to generalize beyond your training data. There's another really nice example that this actually happens in large transformers as well. So this paper basically noticed that if you create a transformer model and train it on orbits of planetary data, if you give it a long context length, which only increases the representational capacity of the model, then it chooses Kepler's laws, which don't generalize particularly well. But if you constrain the context length to only 2, then you get a Newtonian model, which actually learns some fundamental underlying dynamics, which generalize better. So again, the model size that you choose and the inductive bias that you get are related to each other in our current training procedures. So if we want to do better than current deep learning, I think we need to address 3 problems at the same time. We need a procedure for selecting between different generalizations. We need to get working continual learning methods so that we can mitigate the risk of making strong out-of-distribution generalization. And we also need some kind of mechanism for being able to adjust the model capacity so that it actually can learn from this new information. There's a question at the back.
Yeah, sorry. This is more related. Zero shot.
Sorry?
Zero shot mechanism.
Well, I guess what I'm saying is that the zero-shot mechanism is kind of unfair, right? If you want to do out-of-distribution generalization, and you say, okay, well, how are you going to generalize to something completely that you've never seen before? Then this current train-test split is unfair because, you will make mistakes when you encounter things that are generally new. But the solution is, and the intelligent solution is, that you want to adapt to it, so you don't make the same mistake many times. Another question. I do need to get through this quickly.
I mean, the issue with AI safety is if you take the wrong action once and then you don't get another chance. You never get. You sort of mess with the correction mechanism.
That's true. So you always need to be cautious, right? But this is an inherent risk with doing things that you've never seen before.
Yes.
Right. You cannot get away with that. So we need to deal with that as well as we can. And adaptivity is one way of at least being better than having a static model. But we can talk about that later. Yes. Okay. So my point is that all these problems are interconnected and they actually must be addressed together because you can't. So the example of the transformer with the short context length and long context length, it showed that you can't address the model size problem without also influencing your inductive bias, and you can't address the inductive bias. How should you generalize out of distribution without also looking at the model size problem? So you have to do it together. So what I want to tell you about, I won't be able to explain exactly how it works, but I want to give you a taste for it, is a method that I've been working on finding inductive bias, so distinguishing between inductive biases that generalize out of distribution, finding the weights of a model, so that's just your learning algorithm, and finding your model size, all with a single objective function. Now, it turns out that this problem hasn't even been solved for single layer neural networks. So we have to walk before we can run. So let's start by finding a clear answer for a single layer neural network. So here, and I'll basically give an example of the method that I'm working on and the behavior that it has relative to current deep learning approaches. So let's take a case where the predictor is a single layer neural network. So you've got some basis functions here, and you've got some weights that sum them together, and then you get your function. And here I've got some input weights. So Zm are the weights from the input layer to the pre-activations. And then theta determine our inductive bias here. They basically change the shape of all of the basis functions. And then the specific example that I'm going to choose is going to be a model that can choose between basis functions that look like this. So they're either wide or narrow local basis functions, or that look like this, which have a periodic structure in them. So the model actually has two different inductive biases that it can have. Either it can only rely on local smooth generalization, or it can choose functions that are periodic, which might allow you to generalize really far away from where your training data actually is. Now the goal is to have a single objective function to find both the hyperparameters that control whether our model looks like this or whether our model looks like this. So these are the weighting factors of those hyperparameters. Also the period and the width of these basis functions, so the wiggliness of the function are all these hyperparameters. We want to find the size of the model, so how many of these basis functions we actually sum. And we also want to find the weights that control the function at the same time. Now, because I probably won't have time to get into depth about how the method actually works, I want to give a little demo of what a working solution looks like. And the interesting thing is that from this one objective function, which basically is MDL, you get a lot of behavior that people are interested in. So you get growing and pruning behavior, and you also get dropping behavior. And specifically what we'll see is that the size of the neural network that we end up having actually is highly related to how we generalize out of distribution and the inductive bias. So here I've got a little data set. And I initialize our method with a single neuron, single basis function that we place here at the black point. And then what I'll show you is a little animation of what happens when I train. So if I look at the first iteration, the first thing that the method does is it adds a whole bunch of neurons so that we fit the training data as well as we can with the width of the basis functions that we have initialized at. And then as we train, we see that the function gets more and more complex, more and more flexible, until we get a fit that looks pretty reasonable. Oh yeah, the blue lines, by the way, are uncertainty. We get that as a byproduct of our method. So what we see is that to fit the training data, we actually see that the number of neurons increases. Now remember that our model could also become periodic. So if we keep training, what we get is something that looks like rocking dynamics. Eventually, the model realizes that the training data are actually periodic. And one interesting thing that we see is that when the structure is actually found, the number of neurons that you need to represent the solution shrinks significantly. So not only have we found a better inductive bias that fits with the training data and seems to be confirmed everywhere, that generalizes out of distribution, and it turns out that from an information theoretic point of view, this solution compresses the training data better. But we also get a computational benefit from this compression. It's not just compression in terms of some information theoretic quantity that you can compute. It actually allows you to use fewer neurons, fewer compute units. Here's another little example that starts with memorizing training data. We can also start with really narrow basis functions, which don't generalize at all, but allow us to fit our training data. And the first thing our method does is it adds one neuron per data point. So it memorizes the training data. And then as we learn, it first finds this smooth solution and reduces the required number of basis functions, number of neurons, and then it finds the periodic solution, and the number of neurons shrinks even further. Okay, so why is it hard to solve this problem? What's wrong with actually minimizing losses? Well, the reason why it's hard to solve this problem with current deep learning solutions is because deep learning currently only reduces the fit to the training data set. And it works if you're trying to adjust your weights given a fixed inductive bias and a fixed model size. But if we actually try to learn the model size and the inductive bias together with the weights, what we're going to choose is a model that is least constrained and can fit the training data really, really well. And it just also adds capacity so that it fits the training data better. So what it does here is it actually adds 1 neuron per data point in the end. You get a perfect training fit, but I hope you agree that this won't generalize particularly well. It also won't compress the data very well. But that's what our current methods will prefer to do. So yeah, the maximum likelihood method is not sufficient. Restricting the model size never improves the loss, so you're always encouraged to make your model bigger. Narrow basis functions also allow you to be more flexible and fit your training data better. And the periodic structure is also not reliably found because the periodic structure fits the training data equally well as the smooth solution that we saw. So once you're in a solution like this, there's also no gradient signal to make you learn something else. So we would call this overfitting. Okay, so what's the solution? So yeah, the community where I come from is basically the Bayesian community, but there are tremendous overlaps with MDL and algorithmic information theory. And they both basically naturally lead to a way, well, they both basically prescribe that a solution to these inference problems is to try and compress your data rather than just fit your data. So basically, like I said, I believe that the theoretical frameworks that we have are basically right. MDL tells you the right thing to do. Bayes basically tells you the right thing to do. There's only one complication. And that's, but let's see what that complication is. So the Bayesian answer is basically that we should just do Bayes' rule on all our unknowns. And most of the time in deep learning, people are interested in getting uncertainty, but I actually think that's less interesting than the Occam's razor effect that you get from Bayesian inference, which you get by asking for the posterior over all your unknowns, right? So in Bayesian deep learning, people usually just focus on their parameters over their weights, keeping their model size and their inductive bias fixed. But actually the cool thing about Bayes is that it tells you what to do if you want to find any parameter. So Bayes tells you you should just find the posterior over the weights, the hyperparameters, and the model size. And you can make some approximations to make this a bit more practical. So if you approximate the posterior over the hyperparameters, then basically you find that a reasonably good approximation is to maximize the log marginal likelihoods. So you might recognize this as a 1-part Bayesian mixture code to find your inductive bias and model size. And then you find your weights using your usual posterior, and that gives you a way to predict. Now, interestingly, this method, which is what you naively would get if you simply applied Bayes to all your unknowns, this actually has a few pathologies, but you can fix them, and it makes your model better as well. So basically, the key thing in the way that I'm arguing that we should address this problem is that we should be using models that are defined with an infinite number of degrees of freedom, but then approximated with only a finite number of degrees of freedom. And this gives you tangible benefits. So this is something that's been studied in Bayesian non-parametrics before. And the key problem that you solve with this is that, interestingly, if you set your model up correctly, Bayes doesn't actually distinguish between models of different sizes once your model is large enough. So basically this, and this is the same with MDL. So this is a property that you see if you analyze the Bayesian 1-part code, which is that if you set your model up correctly, then the amount that your model compresses your data does actually not depend on your model size anymore. So that actually means that you don't have a principle for distinguishing between whether you want a model of size 5 or a model of size 11. But the problem is that these models do predict differently. So you still need a principle for determining, for distinguishing between which one of these model sizes you choose. And what we've seen here is that Bayes doesn't give you an opinion in the same way that the training loss doesn't give you an opinion about models that predict differently but fit the training data the same. So what I think that this is telling us is that Bayes is actually telling us to use an unboundedly large model. So it's telling us to take a limit of an infinite number of neurons. And it turns out that this actually has some other benefits. This is something that's done, and you can mathematically do this. It's done in Bayesian non-parametrics. It also improves your uncertainty, right? So if you use a finite number of basis functions, then you can only fit data in a particular region, and you also make incredibly certain predictions in regions where you don't have any basis functions. But if you add basis functions in those regions, you can become uncertain there. And you can even take the limit of the number of basis functions to infinity. And as I showed earlier with that Occam's razor plot, you don't get penalized for that in the compression of your training data. But it does make your predictions more safe, more robust, more cautious. And it also fits with intuitions from double descent, which argues that large models are easier to train and overfit the weights less. So you can do this, and you get a Gaussian process. It fits the problem setup that we had earlier, the form of our single layer neural network. Gaussian processes basically are a single layer neural network. They're just a different representation. And it solves our problem for finding the hyperparameters. The protection from Bayes gives us the behavior that I showed earlier. It finds the weights as well, but it does something weird with the number of neurons. The Gaussian process point of view basically tells us that we should use 1 neuron per data point. So although it compresses in terms of information theoretic quantities, it does not compress in terms of computational units. So that's bad, and that means we need 1 additional principle to answer all these questions. So yeah, so our model grows as we see more data, but it does so by memorizing all our data. So we don't get the computational benefit of compression. Now, 1 principle for selecting the model size comes from turning this 1-part code into an approximation by a 2-part code, which basically allows us to define a non-parametric model with an infinite number of degrees of freedom that has this nice uncertainty properties, but then we approximate it with a much smaller number of degrees of freedom. And it turns out that you can always get very close. You can prove this. And so what the criterion then becomes that that then leads to the method that I showed you early on is to minimize the model size, so minimize the number of basis functions, subject to a constraint that we still compress the data near optimally. And that is basically the principle that gives you the method that I showed earlier. So it's a little bit finicky to show exactly how it works, but the point is that this 1 rule that we can summarize in 1 sentence is very simple, but it gives interesting adaptive behavior. So not only does it give you the growing and shrinking and grokking dynamics that I showed you earlier, but in continual learning, it also gives you nice behavior. So here I've got 3 examples of continual learning problems. One where we get constant novelty with every single batch, the range of input points that we see grows. One where we get IID data, and one where we have outliers. So it's a heavy-tailed distribution. In the case where we get a constant batch in a new region every single time, we see that the number of neurons grows linearly with every single new batch. In the case where we slowly fill in a particular region, then the novelty in our data asymptotes and the number of neurons converges. And in the case where we see outliers, we might converge at first. And then suddenly when we see new things, our model realizes that it needs more capacity and adds that capacity. So to conclude, basically Bayesian model selection works for finding inductive bias, but not for model size. It's consistent with minimum description length because it measures how well you compress your training data, not how well you fit it. Approximate Gaussian processes give all the benefits of this non-parametric models, but give you a way of decoupling the model size. It allows you to define an infinitely large model and define the learning solution of that, but then represent it with a small model that's guaranteed to find the same solution. So that also gives you all the benefits of double descent and predictive good uncertainty without losing the learnability that you get when you start trying to learn small models. Once you've got this parameterization, that also gives you a principle for selecting your model size, which is basically compress your training data with the smallest number of neurons possible up to some tolerance of the optimal compression. And that leads to what I would say is intelligent adaptive behavior on the level of the neuron to problems that you might encounter. So I think we can have our cake and eat it. And I think that we basically know the quantities that are prescribed that we need to compute. But the big challenge is how do we actually compute these quantities for realistic, deep, large neural networks? And so we've had some, as I mentioned all the way in the start, with our work on architecture search, we've had some success already with networks. So, there's evidence that it's possible, but there's a lot more work to be done. So I'd be very curious to hear your opinion, and I'm happy to chat later on as well.